Yeah.
Yeah, because I'm gonna say a lot of important things. You might want to take a look at it again in the future. So, yeah, so the purpose of this of today will be to let you know how to look for applications of quantum machine learning on papers, because there are a lot of papers out there on quantum machine learning. We focus on a specific type of quantum computing approaches to quantum machine learning. So I need to tell you like how to distinguish between them. Basically, because we have access to a specific type of quantum computers called superconducting computers. And these are gate-based quantum computing. I looked at some of the papers that I received from Samuel, and some of them come from another approach to quantum computing, which is called quantum annealing. Uh, we don't have access to that. We can do some approximations of annealing on superconducting quantum computers, but the idea is try to use the quantum computers that we have access to do quantum machine learning. So let me start by show you some. Oops. Okay, no. Apparently need to update this. Can you see the paper I'm showing?
Yeah.
Okay, cool. So I was looking at some of the papers that Samuel sent. So this one, as you can see here, so this one says the D wave. So this QA means quantum annealing. So that's one of the computers we don't have access to. I mean, that doesn't mean that we should discard this paper completely, but at least at the IQ, we don't have access to quantum annealers. So that's one thing to look for. D-Wave is the biggest company on quantum annealers right now. So if you see either one of these two, you can start thinking that maybe you should be looking at another paper. Um, also here they use the SVM. So this machine learning algorithm, and apparently there are some places inside the SVM algorithm. This I lost the name, support vector machine, that you can do with a quantum computer. So at some point in the SVM, you have to invert a matrix or get some values from a matrix, like eigenvalues or eigenvectors. And this you can do easily on a quantum computer. The thing is that we will need to decide the approach the project is going to take, because for one thing is these type of algorithms, they require what is called a state preparation, and this is costly in terms of quantum computing resources. So that's one thing to keep in mind. So whenever you see QSVM, this quantum SVM that requires this thing, so and this approach is mostly for long-term quantum computers, which are also called fault-tolerant quantum computers. And right now we're looking for algorithms that are suited for noisy intermediate scale quantum computers. So this algorithm, this QSVM, this requires either quantum annealers or fault tolerance superconducting gate-based quantum computers. So yeah, the idea is interesting. Basically, is trying to use this variation of SVM to do classification with it on. I'm not sure what kind of data they use, but anyway, so that's for this paper. Let's move on to the next one. Yes. So here are a couple of things I need to confess. So tensor networks is a whole topic on itself, and I'm not an expert on tensor networks. I know a few things, but it's a complicated mathematical and physical merge of topics. Um, Tensor networks are mostly used to simulate quantum computers and to reduce computations that are based on linear algebra operations. So that's why you see here that they use GPUs to do this kind of operations. Basically, because GPUs and other languages like other libraries like PyTorch or TensorFlow, they allow you to work with tensors and to compute derivatives with respect to these tensors. So that allows you to do something called differentiable programming. So that's one of the approaches one can take. In terms of the quantum machine learning approach, I'm not sure what this paper is doing. Let me see. It seems like they do. Okay, this looks like segmentation. Yeah. Okay. Yeah. Also in here, yes. So this is another approach you can take: physics informed neural networks. This can get technical on the physics approach. I can help with that. It's basically creating a classical neural network in which the loss function gets information from the physics of the problem you're trying to solve. But here I'm not sure where's the quantum part. Let me just make a small search. Quantum inspired tensor network for compressing trainable parameters. Yes, okay. So in this part, you can see that this quantum inspired tensor network, what it means is so tensor networks are used to model a lot of things in physics. One of them is quantum circuits. Well, that's one of the approaches they can make. Again, here in this paper, they don't use superconducting quantum computers or gate-based quantum computers. And if you take a quick look at the paper and you look at the figures, you can see there are no circuits as the ones that I showed you on the last workshops. So that's one easy way to look um, for circuit-based or gate-based quantum computing. So that's for this paper. The other one, I think this one, if I just scroll down, you can see there's a circuit here. So that's a good way to look for the type of quantum computations we would like to do. Now, in this paper, they used an hybrid approach. This is very common in practice and in research right now. So basically, you put your data into a big neural network that is already trained. You take the output of it. Maybe you just chop the last layer and do some transfer learning to input the data into the quantum machine learning model. This works like a charm, but the thing is that basically the neural network is doing all of the work. So the neural network, the capacity of the neural network is doing all of the work that the quantum machine learning algorithm is required to do. This is not bad. It's just to tell you that we can put them together, but if you expect good results from this, you will get them, but just because you have a neural network in the middle, like a pretty big neural network. Um, Yeah, so here you can see they're using, I think this one is the uses data re-uploading. Yes, data re-uploading. Uh, so what this means is that in your circuit, I don't know if you remember in the quantum machine learning workshop we did 2 weeks ago, you can put the data like in a layer fashion on your quantum circuit, and you can just add more layers in which you put the data. So this is what you call data re-uploading, with some few other technical details that you have to put in there. But that's basically the idea. So you have to put more and more times the data. This apparently works if you do like a layer fashioned quantum circuit for quantum machine learning. Here, yeah. So in this case, you can see in this figure 4, This is a multi-qubit n-layer quantum machine learning network with data re-uploading. So basically, this L1 has the data uploaded, then you repeat it several times, and it's basically the same layer that you repeat. So it's the same idea. So in different applications, what will change is the gates that you use, the number of qubits you use, but it's basically the same idea. So here again, you have without data re-uploading. I think this is, yeah. So in the figure 4, you can see you have U of phi1, U of phi2, U of phi3. This is the data. So you can see on the layer N, you also have the data there. And the one on the right, this has no data re-uploading. So you have the data only on the first layer. And the layers that you repeat, they don't have the data. You have only the trainable parameters. So that's one of the approaches you can take. But also keep in mind that since today's quantum computers suffer from a thing called decoherence, you don't have like a unlimited time to put the data several times in there. It's been shown in theory that this helps, but with today's quantum computers, we have to put attention into this because this might not work as good. So this paper seems all right, but again, you need to use, as you have here in this figure, you need this big neural network to reduce the size of your image. So this image does not go directly into the quantum circuit. Uh, Actually, let me, Maria Schultz archive. This researcher is from Toronto. She has a lot of papers on quantum machine learning. They're pretty good. Let me show you how this one. So the effect of data encoding on the expressive power. If I go to the paper, then you can see she does an Fourier analysis of what happens to the data when you put it several times in a layer fashion into your circuit. So that helps in theory. Let me see what else I can show you. Yeah, and she does some simulations. But again, these are this is curve fitting on simulations, depending on the amounts of times that you uploaded the data. So you can see if you uploaded one, then you don't fit the actual curve that you want. If you do it 5 times, then you can see you have a pretty good accuracy on fitting this curve. But again, I think these are just simulations. So these are not run on today's quantum computers. What else do you have here? Yes.
Marco, could you post a link to that paper in the chat, please?
Yes, definitely.
I just put it in the chat.
Thank you.
Ah, perfect. Yeah, teamwork. So yeah, this paper, it's actually Maria Schultz is a machine learning specialist. So she approaches these problems more from the machine learning approach. So you can see she looks at how you can fit the data, how you have sometimes she even looks at the expressibility of the models, things that you mostly do on machine learning, classical machine learning. But she tries to adapt that to quantum models. This could be a good paper to start. Let me just see if she's using a gate-based. Yeah, okay. Yeah, actually, yes. So this is a circuit. So as you can see, this is one of the circuits. Well, the shape of the circuit should remind you of all the workshops we've been working on. So you have all your qubits start on state 0. The wires represent each qubit. These represent like gates on several qubits. We know that we have only one 2-qubit gate, which is the CNOT gate. But what this means is that inside each one of these boxes, you have all these qubits are connected by CNOTs, so they interact. So yeah, so this is a good paper to start. What else can I tell you? Oh yeah, there's another paper from this author. Quantum embeddings, training. There's another one where they train the embedding. Quantum embeddings, I think is this one. Yes. Okay. So in this paper, so what they're trying to do is the following. Let me go back to the figure I'm looking for. Yes, this one. So let's say you have your data like this. So again, what we want to do is find a way to linearly classify, linearly separate this data. In this case, this is one-dimensional data. We don't have a way to separate this linearly in this space. So we would like to put it into quantum feature space and then try to separate the data in this space. Then this circuit is just a 1-qubit circuit. You can see that this x1 is repeated several times. So x1 is one of the samples from the data. And then you have trainable parameters. So theta 1, theta 2, theta 3, theta 4. So this one uses data reuploading. And then you train these parameters theta 1, theta 2, theta 3 to try to classify the data in this space. Now, this thing with the traces can get technical. You can ignore it for now. What's important is, so this is the Bloch sphere. Now, remember that I told you that when you have 1 qubit, you can visualize the qubit state on a Bloch sphere. In this case, you have the data. Once you train all of this, you can see that the data on the blue region is correctly classified. The data on the red region is correctly classified after you train this. But this is a very small data set. So this is a one-dimensional. So that means you have one feature on per sample. You can do this analysis. It looks cute on the Bloch sphere because you can plot everything, but it's not as useful. It's not as applicable to real-world data because you will not be able to visualize this. So that's one thing. Another thing they do is here. So again, this now they use the original data. These are high dimensional images. They put on top of that ResNet 512. So for those of you who don't know, this is a pretty big neural network. It has 512 layers. It's a convolutional neural network. It's already trained on tons of data. And these red arrows, red edges here means you train the last layer. So basically you chop off the last layer of the neural net, you put a new one, and you train it together with the parameters on the quantum circuit. Now, these are high dimensional images, and you reduce this to a 2-dimensional vector. So each image passes through the neural network. Now, it should be clear that the neural network is doing all of the work to produce this x1 and x2 so that when you put it inside the quantum circuit, then you can separate the data. Now, this is more like a proof of concept application. What you do is you can plot what happens to the data here because you reduce it to a 2-dimensional vector, so you can plot it in a 2-dimensional plane, and you can see what's happening to the data after the training. Now, the neural network, it's producing this x1 and x2. So what you see in this yellow rectangle is how the data is being produced during the training by the neural network, not the quantum circuit. So step 0, so you can see the data is basically noise. But after the training, you can see that the neural network learns to put the data in a periodic way. And this is because the gates that we use on the quantum circuit have a period. So their rotation, so you have a period always of 2 pi. And here you can see that the points are the neural net learns to put the data in this way, so that the quantum circuit can exploit this embedding. So again, this is one of the approaches to do it. This can be explored with higher dimensional circuits. That's the one thing I've been wanted to try for a while, to be honest. To put a big neural network and a big quantum circuit, because most of these are like in this case you can see there's a pretty huge neural net and a very, very small quantum circuit. But right now we have a pretty huge, not huge, but bigger quantum computers. So we can play around with this deep learning and quantum machine learning approach that is being merged. That's one thing we can try. This paper, I think Tanya already put it there. So, thank you. Yes. So yeah, the idea is so here what they explain is you can see that they put the images inside of a cat, meaning that they put the image into a quantum state, but it is not the image that they put into a quantum state. It's the vector that is the output of the neural network that is then put into a quantum state. So again, this presentation looks cute. It kind of motivates the idea of putting this into a quantum space, quantum Hilbert space. But it, yeah, I think it can be improved, mostly because we have now bigger neural networks and bigger quantum computers. So we can definitely exploit this. This is one of the approaches I would like to take if you're interested. So yeah, so these are two papers that are pretty interesting that we can start reading. And this is basically what they do in this paper. So this is a paper that Samuel sent me. I'm not sure about the data they use. Oh, I think it's here. Yeah, so this is UC Merced Land use dataset. So I don't know about this dataset, but
well, it's a quite a standard data set. It's airborne imagery, and it's a long cover classification. So each patches you see on the top left are classified in terms of long covering.
okay.
Yeah, it's pretty standard.
Yeah. Okay. I see. Good. So the results are pretty good. But again, probably the neural net is doing all of the work. But again, actually they use VGG 16, which is smaller than the ResNet 512. But okay, so that's another thing. Now let's go. So this is the another author that Samuel sent me. So if I just look for quantum. So yeah, if you look at the first one is a quantum annealer for subset. So as soon as you see quantum annealer, you can discard it. I mean, you can give it a try, but I will not be able to help you with it because I know just the very, very basics of annealing. The next one, classification of remote sensing images with parameterized quantum gates. So yeah, parameterized quantum gates, this means variational circuits. So is this one of the ones that I already looked at? No, so let's have a look at this one. Should I log in? Okay, I can. Yes, so let's look at what this paper is doing. Hybrid networks. Yes, this is another thing we can try. Let me show you first. There's a Qiskit textbook. So if I go here, learn quantum computing using Qiskit, and if I go to chapter, I think it's chapter 4. Yes, hybrid quantum classical neural networks with PyTorch and Qiskit. Good. So let me give you a small overview of this. Where's the thing that I want to show? Okay. Yes. So the idea is that apparently Qiskit and PyTorch are compatible right now, and you can plug in into a classical neural network. You can plug in a quantum layer. This will not make the neural network work better. Actually, it will worsen the results by a big margin. But it's one of the things that we can try because we can combine it with the PyTorch um, how it is called, automated differentiation. Here, okay, so this is one small example. So you can see, you start with classical data, this x1, x2, x3. You put a linear neural net layer there. Then you apply some activation function, this sigma. Oh, should I assume everyone is knows what a neural net is? I think I shouldn't, by the way. Is there anyone here who has no idea what a neural net is? Is that a yes or no?
I think you can assume that everybody knows neural network.
Yeah.
Yeah.
Okay. I mean, if not, you can just assume this is an algorithm that helps a lot with machine learning in general. So yeah, so you plug in one of these modules from PyTorch, and then you can use these outputs, so this H1, H2 from your neural net, plug it into the rotation gates of a parameterized quantum circuit. Then you can do quantum measurements on these qubits, on these quantum states, and use the measurements or the probabilities after the measurements to put it into another layer of your neural net. Now, in this case, this will be like a linear, like a perceptron, because in this case, you have a sigma. I think this, they're assuming it's just a nonlinear function, but you can assume it's a sigmoid. So you can do binary classification at the end with this output. Yeah, so backpropagation is the algorithm that helps that we use in PyTorch and deep learning in general to compute the gradient with respect to parameters to do the optimization. This has been done also for quantum circuits. So you have this trick which is called parameter shift to obtain the gradient of a quantum circuit with respect to the rotation parameters. All of this works really good together. What else do they have here? Okay, yeah, so here it's how you do it in PyTorch. So you can see you have to put actually this is Qiskit and PyTorch at the same time. So you have to work around your forward pass in which you can add a quantum circuit. Then you have to create the backward pass that it's going to give you the. So in this case, what they're doing is this parameter shift rule to obtain the gradient of with respect to the quantum circuit. And I guess with respect to the classical part, you just use PyTorch because it's already built in. Yeah. So here you can see there's the code to start working with that on a small example. Here they use the MNIST dataset. Now, remember that, oh no, actually this at the end, I think they have a classical layer. What does this hybrid function does? So it sends the result from a tensor. Okay. So yeah, what they want to do here is binary classification. So that's what they do this part here. So what you're taking is a few number of samples from class 0 and a few number of samples from class 1. Now this is this gives you the indices from your data. Then you take this data, and that's the data you're going to be using to train the model. Here, they're only showing some of the samples, so you have only zeros and ones with the labels. You prepare the data to be trained. Oh no, actually this is the test data, so you get the other samples to test the model. And here is the neural net. So you instantiate, you create a class that is doing, how do you call this? Is inheriting from this nn.module from PyTorch. And you do everything as you would in PyTorch, and you can add this hybrid layer that we added before. Of course, you have to add how to run the circuit. So this thing here is the either the simulator or the real quantum computer you'll be using. And on the forward pass, you do it as you would in PyTorch, and you call this quantum layer, this hybrid layer, as you would call a layer from PyTorch. So it's pretty simple once you build this this hybrid layer that is built here on top. This one. And if you look at the results, I think, yeah, so this is the evolution of the loss and the accuracy. Now, so this is the training model, the training performance. The test, you can see you have 100% accuracy. It's a pretty simple data set. Plus, you're using a neural net also that on itself can achieve 100% accuracy pretty easily. So these are the predicted labels from the model. And okay, here's not the other thing, but there's I don't remember what it is, but they compare this to just completely classical neural network, and the classical neural network, even smaller than this one, behaves way better. So that's one thing we can try. That's what they do in this paper. So this picture, as you can see, it has now, it starts with a quantum circuit. Then you create, so this, whenever you have these two brackets inside the thing that has a symbol, this y sub l, it doesn't matter what it is. What it matters is that it has a small hat. I don't know if you can see it. So whenever you see a symbol like this, so a letter with a hat and then two brackets, that means an expectation value of something. So that means you create a quantum circuit, you obtain the expectation value, and then you input the expectation value into a neural network. So, and apparently that's not the whole story. Let me see if they have something else. Yeah, okay. Yeah, actually it's in this image. So again, they use a VGG to do dimensionality reduction. So they take, their images are 64 by 64 color images. They put it into a VGG, they reduce the dimensionality. So they have a 4x4 tensor. So again, probably the neural network is already doing all of the job in reducing the dimension here to give you the data that it's already going to be easy to classify. So you put it into a quantum circuit, then you compute expectation values, and then you put another neural network. So, and this neural network will have its own loss function. So this will help you train both things. So the weights on the neural network and the parameters, the rotational parameters on your variational circuit. Okay. Now here, what are they doing? Yes. So look, here they have an example. So they have the input image. They pass it to a VGG neural net. They reduce the dimensionality. They pass it to a quantum circuit. Now here's the instance of the quantum circuit. And here you can see, so first of all, whenever you see gates joined by by a line, like a vertical line, and it's not a CNOT, then this is costly because this will require at least 2 CNOTs. CNOTs are costly and they introduce errors into the quantum computations. This doesn't means it's bad. This is just nice to have it on mind whenever you look at this. So from the first look, this thing it's going to be costly. It's probably can run on today's quantum computers. So what you do is once you put this, you create this circuit, and again, you launch this circuit several times. You measure the expected values, and then you put these values into a neural network. So these are the outputs here that you have on the green and blue nodes. And then you use the loss function to train these parameters. Here you see the algorithm. What does it says? Eurosat data. So I don't know what this is, but it's probably data that looks like this. Yes, Eurosat training images. So the output should be either one of 2 classes. So this means you have binary classification. Dimensionality reduction. So the classical layer means you use a VGG neural network. Then to produce these 4x4 images, then you have this quantum layer. This PQC probably means parameterized quantum circuit, which is the same thing as a variational quantum circuit. These are like synonymous. Then you put the reduced image into the parameterized quantum circuit, and then you train. So you put this into a training loop. And then you test the algorithm into the testing images. So that's basically it. Yeah, okay, maybe I can tell you a little bit more about this. This is another approach that people are using right now. Oh, look, here they do the comparison between the 2 approaches. So they do dimensionality reduction with the VGG. And then from there, they used parameterized quantum circuit. And independently, they use a fully connected classical layer. So this is a classical neural network. And so depending on the classes, you have different performances. You can see that the neural network, the classical neural network beats all the times this one. Downsampling, I'm not sure what this is. Downsampling. Okay, we'll need to look at the details, but apparently here the quantum circuit performs better, but just in a small approach, in a small small numbers. Okay, so here's 20%. That's not that small, but anyway. So going back to the quantum approach, so this part here. So again, you have a hat, so that means you have something that is quantum. Every time you see an X or a C or a Y with a hat, these are the Pauli matrices that so this means measurements along the axis, the different axes on the block sphere. And you can produce Hamiltonians. So these are observables. So these are operators that are more complicated, but you can build them in terms of these polygates. In this case, they're using this polygate that is, it comes from some ideas from physics, some physics approach to build this thing. What this will give you is, since this is an addition of several terms, what you can do is use linearity of quantum computations, and then the expected value of this H can be decomposed into different expected values with respect to the terms in this sum. This is something that at least the first time I saw this was on quantum chemistry, where you need to measure the quantum state of molecules on different axes to to have the expectation of the energy of the molecule. Here is the idea is something similar, but you don't have the analogy to energy or molecules. Sorry, to the energy of the molecules. But again, also these parameters apparently you need to get them from somewhere else. But the idea is that since you have this thing that is called a Hamiltonian, the terms that you have inside of it, you can compute the expected value for each one of them. So that will give you several expected values, and you can use all of these values to put them into a classical neural network. So in this case, that's what they do here. So in this case, you have two input neurons in this figure from just one quantum circuit. Now, remember that if I give you just one observable, you can compute only one expected value. But if you play around with different observables, you can compute different expected values. So in this case, let's say they measure two different observables that gives you two values, two expected values. So these are two numbers that you can input into a neural network. So that's another thing people are trying right now. So this will be a good paper also to start looking at. This classification of remote sensing images. Let me see. I think I need to go back. I think I should probably look for the author. Okay, so I'll look at his archive. He has only one paper. Okay. Okay, I think I lost him. Let me see. Yes, here you are. Okay. Okay, we were looking at his papers. So this is another one. Natural embedding of the Stokes parameters of polarimetric synthetic perturbator images in a gate-based quantum computer. Okay, again, so this is the keyword we're looking for, gate-based quantum computer. Let's look at this one now. There. Let's see what they're doing. Okay, I'm not sure just from the images. Okay, I'm not sure what they're doing here from a first look at it, but it seems they're doing something complicated. I'm not sure what this drawing means. Here you can see you have a quantum circuit. So you have some gates, some parameters that you can train. Okay, so look, yeah, I think they're doing some parallel quantum computing. So they put the data into one circuit, then they parameterize this circuit, and they compute one expected value. Then they do this in parallel with the different quantum circuits. So that will give them different expected values. And then they use these expected values to do a prediction. So again, it's the same idea that you can measure different expected values on different instances of your circuits. Network for the classification. Okay, so this is quantum dataset, QML network, conventional layer of neurons. Yeah, okay. So in this case, what they do is they start with a thing called quantum dataset. So basically, a quantum dataset is points in a Hilbert space. So this is a set of quantum states. Then they put a quantum machine learning model. So this means a trainable variational circuit. They output that as expected values. And then they use a conventional layer of neurons to do a prediction. So as you can see, is the same idea. So you play around with quantum circuits, expected values, and classical neural networks to merge them and to look at data and see what happens. And this is basically research today in quantum machine learning. So mostly they use deep learning. There are people who's working on this that they're not using deep learning. That problem is way harder. And again, it's probably because if you put a neural network, probably the neural network is doing all of the work. So this paper also looks interesting. Let's see. Quantum. Okay, the third one says quantum annealing. So we will not look at it from the beginning. Look at the next one. Assembly of core set of Earth observation images on a small quantum computer. Let's see if they use gate-based first. Okay. Oh, I think here, yeah, they're looking at the iris dataset in this case, which you already know. Okay, look, I found a keyword there. So again, D-Wave QA. So D-Wave is the company that works on quantum annealing. So they have this QA also, which means quantum annealing. So that means that this approach we will not be able to do it on the computers we're working with. So I'm gonna discard this one. The next one says quantum annealer. The next one says quantum inspired tensor network. I think we already looked at this one. Quantum transfer learning for real world small and high dimensional datasets. Let's see what this is doing. I don't have access to it. Okay, here's the archive version. Okay, we already looked at this one. The next one is causality for remote sensing, core set of on a small quantum computer. Let's see if they use annealers. Yeah, okay. So now in the abstract, I found D-Wave and QA. So we can discard this one. We already looked at this one, and this one, and this one. Okay, so that's for this author. There are some interesting approaches there we can start working on. So that's one way to do it. Let me show you now some of the papers I was looking at. Here we have, so these are two review papers. What they do is they look at the most approaches that that people work on for quantum machine learning, either using deep learning or not. The thing, so if we're looking for publications, I will say we can try to do something like this, either with deep learning that is very creative, or we can ditch deep learning and try to do something directly with the quantum circuits. Now, the advantage of this is you don't need what will be the advantage? Okay, so if you have students, I know you have some students like Xiao that know their way around deep learning. So you will need to look at how to merge this with deep learning and quantum circuits. But also, if you have only quantum circuits, the training loop is going to be simpler and faster. That doesn't mean that you're going to have a better convergence. But also, if you have a quantum circuit that works good, and good means in a binary classification, like let's say above 65% accuracy, and it's running on a real quantum computer, then that is publishable. So, and that's what we're looking for. So this review paper is from 2022, and the other one is from this year. So this is going to be interesting. Let's look at the other one first. Let's see what they do. So yeah, I think they have a whole diagram to explain how they look at the literature, how they filter the papers they're gonna look at. So these are the questions they ask themselves: what type of algorithm is used? Do they use hybrid or pure quantum algorithms? What are the applications? Are there experiments carried out on simulator or real quantum devices? Inclusion and exclusion criteria. So the solutions provided by the articles are either applied in software or can be simulated or implemented in simulators or quantum devices. This is because there are a lot of papers right now that are completely theoretical. So for instance, I think I told you about the Shor's algorithm that breaks the RSA encryption from credit cards, but this needs millions of perfect qubits. So this is so you can say that that is purely theoretical work. So that's one of the things that they look at in their review paper. The papers are available to download, so I think that's something we would like to see, like papers that we have access to. Papers that are published or preprints written in English or Spanish. Oh, Spanish. Okay. The paper provide a practical solution. What else? Okay, and they exclude also based on this criteria. So that's good. Let's see what they have. Okay, here you have a table. Yes, so these are data sets. I don't know any of these data sets, but they filter them by the papers they look at. Okay, quantum Boltzmann machine. This is basically a Boltzmann machine that is put into a quantum computer. You can ignore the equations. You can look at, what can I tell you? Yeah, no, let's not look at that for now. We'll need to introduce a couple of other things. But look, the ingredients are here. So you have an H. H all the time means Hamiltonian. So that means it's going to be an observable. So you're gonna make a circuit, and then you have you run the circuit, and then you estimate this expectation value. Then you run the optimization over the parameters on the circuit. And here you have this H. This is built on these sigmas. The sigmas are identities X, Y, or Z. So these are poly matrices, and we know we can compute the expectation values with respect to these observables. Now this raw, whenever they have raw, this is something technical that we call the density matrix. Is not going to be important for now. Yes, variable depth quantum circuits. Okay. So here, I'm not sure if they train the depth of the circuit too, but this is something we can look at. Hybrid quantum autoencoders. Okay, okay. So yeah, so I'm not sure if some of you are familiar with the autoencoders. Basically, you have a layer in the middle in which you want to project your data, so that the data gets encoded into this smaller dimension. And here what they do, again, they got creative with neural networks and quantum circuits. So at the beginning, you have an encoder, which is the thing that is going to reduce the dimensionality. You put an encoder, you have a ton of qubits there. Then you get the outputs as probably as expected values or probabilities. You put it into a neural net, and then the output you get it, and you put it again into a quantum circuit. I'm not sure how they use the data to train this, but again, we can start looking at this. Quantum reservoir computing. I definitely heard about this. I'm not sure how it works. Let's move to the next one. Quantum multi-class classification. Okay, good. Yeah, so multi-class means you're not doing binary classification anymore. So you're doing a higher. Probably they do. Yes, look. So at the end, they measure 3 qubits, and they use each one of them to compute an expectation value. And what they do is, I will guess, they use these expectation values to predict on different classes on your classification problem. One thing you need to keep in mind is, okay, so you can see there are a bunch of CNUTs here at the end. Whenever this happens, okay, but no, they probably have they kill the qubits here. So okay, so that's that should be good. So the idea is that whenever you have a lot of CNUTs, like they're all together and they're not separated, but by 1 qubit gates, then you end up with training problems. So you have something that we call barren plateaus. This means that when you compute the gradient becomes exponentially 0. So at the first iteration, that the gradient, the magnitude of the gradient decreases a lot, and then a lot more, and then a lot more, until your gradient becomes completely 0, or numerically 0. So that's one thing to keep in mind. But one way to reduce this is to do mid-circuit measurements, or to reduce at the end with the measurements. So this is probably what they do here. So as you can see, these wires do not continue. So they probably just measure the qubit to try to solve this problem of the barren plateaus. Okay. Okay, this is another one. Look, this is support vector machines with quantum kernel estimator. Okay, again, so this quantum SVM probably requires perfect quantum computers, but this quantum kernel estimator, this can be run on classical and on today's quantum computers. You have pretty achievable circuits that you can run. This is another thing we can look at. Basically, a kernel method is something that requires a kernel that, how can I put it? So basically, it's looking for a separation between your data on a high dimensional space. But you don't need access to this higher dimensional space if you have a description of your kernel. And apparently, we can describe these kernels in terms of quantum circuits. So that's another machine learning approach we can take. And this allows us to evaluate kernels that are not reachable by today's classical computers because of the scalability on dimension wise for quantum computers. Of course, there's the restriction of unitarity on the matrices that we use. Okay, quantum neural networks. Okay, just to tell you, quantum neural networks, they don't really work. But it's basically just a quantum circuit, quantum variation circuit. You have some gates, some parameters, and you train them. They just like to call them quantum neural networks because it sounds cool. Okay, hybrid k-neighbors nearby model. Okay, this is something I haven't looked at, but okay, good. But now here's a simple circuit that they're trying to use. This is called the test swap, and this is costly. Why? Because you have a controlled operation. So these wires, this is not joining only 2 qubits, it's joining 3 qubits. And this is going to be costly in terms of quantum computations. And as you can see here, the circuit that they use has several of them. So this means you will not be able to run this on today's quantum computers. Probably on simulators, but I mean, we can work around with simulators, but again, if you want papers to be published, they better work on today's quantum computers. You can have something published on a simulator too, but yeah, this we can look at this if you want. Orthogonal neural networks. Okay, I have no idea what this is. Let's see if they have something. Okay. So they are constrained to the weight matrices. So basically the matrices inside the neural network. So if you don't know what a neural network is, it's basically a sequence of matrices and some nonlinearities. And what they do is they put a constraint on the matrices. Apparently they use quantum operations to keep track of these constraints. I'm not sure how they put this all together. We will have to look at the details. Quantum fully self-supervised neural networks. Oh, wow, that looks complicated. What are they doing? Yeah, I'm not sure what they're doing here. QFS? What is QFS? Quantum fully supervised. Okay. Yeah, I'm not sure. I've seen these diagrams before, but I'm not sure what they mean here. So these are called lattices. We use them a lot in quantum theory in general, not necessarily quantum computing. So I'm not sure we can do this. But again, if you find it interesting, we can try to look at it. CNOT neural networks. I can tell you from the beginning, this will not work because you use a lot of CNOTs. So look, it's basically based on CNOTs. Okay, sorry, I correct myself. They have intermediate measurements, so this might overturn the effect of the CNOTs on the gradient. I'm not sure how they use only CNOTs to do classification, but anyway. So yeah, this is one way to do it, I guess. Quantum convolutional deep convolutional neuron. Okay, no, this is just too much. So this is basically the idea of convolutions merged into a quantum circuit. Yeah. So for starters, this is not convolution as you know it. This is what they're trying to do is they basically are trying to twist the arm of the quantum circuit to make it look like a convolution. One thing with this is that they introduce quantum pooling layers, and these pooling layers they do intermediate circuit, mid circuit measurements, and they reduce the size of the circuit with these measurements, and this reduces the problem of the vanishing of the gradient. So that's one interesting thing about this type of quantum neural networks, is quantum convolutional neural networks. I don't like when they use deep in this because we don't have really deep circuits right now that actually work. So yeah, this is probably they do it for fashion, just to get more attention, more money. Quantum backpropagation neural networks. Okay. Actually, I already tried to do backpropagation on myself, on my own, on the quantum neural networks, but it doesn't really scale because the quantum circuit grows exponentially. So you cannot run backpropagation directly. They say quantum backpropagation. Okay, that's weird. Okay, I'll have to look at the details, but this is probably not specific to applications. This is probably just trying to train a neural network with a quantum computer. This is what it sounds like. Okay, the next one is feed-forward neural networks. What does that have to do with anything? Okay, so they have some measurements there. They probably plug in this into a neural network, then into a circuit, then they measure. Depends on either probabilities or expected values. They put another neural net layer. Okay, and they do it on a feed-forward fashion, so they probably call this just feed-forward because of that. Long short-term memory neural networks. So these are recurrent neural networks. I'm not sure if I should get into this. So QAUA is one of the famous quantum algorithms we're using right now, but this is for combinatorial optimization. Quantum generative adversarial networks. So as you can see, this gets more and more technical each time, but you can start looking at the circuits. You can see quantum recurrent encoding, decoding neural networks. I'm not sure what they do with that. Okay, application domains. Okay, so here, so you can see now that these are 4x4 images. You can see there's basically not structure there anymore. But they try to do quantum machine learning on this data set, apparently. They can reduce the dimensionality on known data sets. Like you can see here, they do it on MNIST or even CIFAR-10. But again, you lose all of the information on the images. Okay, so this is about this paper, so you can go ahead and start looking at it. This other one is longer, so you can see it has 45 pages. So probably leave that for the next session, or I'll just leave it there if you want to take a look at it. I'll try to read it myself. Let's see what they do. Yeah, basically you have circuits. You have to put in a loss function that will behave good. Here you have again a classical neural net working around with the quantum circuit, and then you put another neural net on top of that. So again, this is basically the idea. Okay, they're trying to put the, yeah, I think there are people trying to do reinforcement learning on quantum models, and it's not working good. It's not working good, by the way. Okay, now they're trying to do that with even bigger neural networks. Anyway, so you can start looking at this one if you want, but I think we covered a lot of things today. I'm not sure if you have any comments, questions so far. You'll probably have more questions when you look at the recording. Also,
it's a lot of material.
Yeah.
Yeah.
So yes.
I think if we check, for example, after the recording, we'll be asking more questions in the next session, maybe.
Yeah, we can dedicate the next session just to questions. For example, you can start reading one of the first paper. I think it's the very first one that Tanya sent in the chat. Is it? Let me see. Yes. Okay, we can start looking at this one. So the first one that Tanya sent in the chat. This is the effect of data encoding. So this again, this works with the small quantum circuits. They play around with neural nets, but they don't really look into the details of neural nets. So you can use them as black boxes, which are black boxes, by the way. So yeah, so let's do this. So for the next session, look at the recording again. Maybe think about questions you would like to ask me. I don't promise I'll be able to answer the questions correctly. I'll try though. We can start looking at this first paper. I don't know if you have any more suggestions.
I have a question.
Yes.
With the things that we learned at first about the basics of quantum, and also the things that we have studied today, and I've also checked the two papers that you sent at first, the review papers. Do you know any sources to fill this gap between the basics that we have about circuits and such things, and also the neural networks and the deep networks that are surveyed in the papers? Because it's a little bit difficult for us to handle what
Yes.
is really going on between them.
Yeah. Sorry if I scared you. So one thing you can try is so definitely this Qiskit textbook. Let me see. So in the Qiskit textbook, what you do is you start with the basic ideas of quantum circuits. So they even give you the code to start working with these things. If you have access to your account, you can put here in try, and you can see. Actually, you don't require your account for this, but for more complicated code, you need your account, and that will open a Jupyter notebook on the Quantum Lab on IBM, if the Quantum Lab is working, because last time it was not working. But yeah, so here, let's say chapter 1 and chapter 2 will help you review everything we saw on the first one or two, for probably the first one. The third one, so the chapter 3, it's more involved, but it's also way more theoretical. So that means you need fault-tolerant quantum computers to run most of these algorithms. So as you can see here, there's Shor's algorithm. This is the factoring algorithm. So yeah, if you want, you can look at it. It's not going to be that useful for today's quantum computers. Chapter 4, this goes into variational circuits. So this HHL algorithm, you can discard it. It's really not used a lot. This is an inverse. It's an algorithm that inverts matrices. So they probably look at SVM, quantum SVM here. Significance in machine learning. Yeah, so again, you can skip this HHL algorithm. These simulating molecules, you might need a little bit of chemistry knowledge for this. I don't think so. But this VQE, basically, it's a variational circuit. So as you can see, this is the variational circuit they use. You can look at the code of how they produce this, how they build the circuit, and how they train them. It should be here. Let me see, optimize. Yeah, okay, so they do the optimization here. So you can look at this part of the code in this simulating molecules using VQE. There's another type of quantum variational algorithms, this QAOA. This is done for how do you call it? Combinatorial optimization. This gets more involved in terms of how you build the Hamiltonian. So, but the idea is the same. So you have a variational circuit, and then you measure your qubits and do expectation values, and you have this hybrid loop. So you compute the gradient and you actualize the parameters. So you can start looking at this. So this is about variational circuits. This hybrid quantum classical neural network, this will help you go into a little bit of the details of how a neural network is built in this part here. So this is what you will need to know for neural networks for now. So basically what you do is you define your layers, and then you do a forward pass. So the forward pass means how the data is processed by the neural network. Here they include this quantum layer, but you can ignore it, and then you'll have a classical neural network. So yeah, I'm not sure. I would like to give you more like a introduction to neural nets because as I said, if we use them, this will be more in a black box manner. So you will like just download the neural network and use it as a function. So yeah, does that answer the question, or do you got the response you were expecting?
Yes, it was comprehensive. Thank you.
Okay, good. Yeah, but don't get don't get scared. I know it's a lot. Don't worry, I'm not gonna be evaluating you or anything. I'll be the idea is that I will be guiding you. So I just try to show you like in general what are the ideas that are being approached right now, and to give you some tools to start reading about it. So yeah, let's have more like involved discussions for the next time. I'm not sure if there are more questions, comments. Okay. This is pretty nice. Yeah, so Tanya did a small overview of the papers we were looking at. So if you want the links, they're on this file that she just sent. So should we stop for today? What do you think?
Yeah, I think so. Yeah, I think,
Yeah.
Yeah, it's enough. I think.
Okay. Okay. Good.
Thank you, Mark.
Yeah, thanks for your attention. And again, just don't be scared. This is going to be it's going to be good. I'll guide you through everything. And if you have any questions at any moment, if you're reading a paper and you get stuck, send me an email. I'll answer you as soon as I can. So thanks. See you next time.
Thank you.
Thank you, Marco.
Thanks.